Okay, so it's 1500 and it's time for gain visibility into workload interdependencies. You have two speakers today, both called Dan, so don't get confused. We have a Dan Rosa and a Dan, well, Vigeland? Vigeland?
Wigand, yep.
Wigand. Wigand. You know, I wouldn't have come up with that one.
Wigand, yep.
Both from IBM. And this is session 2AJ. And please remember to give feedback at the end of the session so that we have something to go on for next year's, hopefully face-to-face at Celtic Manor conference. Okay, so we're on time to start, so I will hand it over now to Dan Wigand.
Yes, very good. So thank you, Anna. I wanted to thank everyone for taking time out of your days to join us. Unfortunately, as Anna mentioned, we're not here face to face, but we do have an exciting new piece of technology that Dan Rose and I wanted to go and talk about. And Dan will drive through a brief demo of the solution today as well as we go through. Our contact information is there, so if you guys have any questions or comments after the session, please feel free to reach out to us as well. So when we look at what the big challenge is, and a lot of it is how we analyze issues that are happening within our workloads. And for a lot of our customers, those workloads are largely a black box, especially when we start thinking about all the interdependencies and how things are connected across the entire workload stack as they're sharing resources and running in that same environment. And for a number of our customers, you know, this is okay. They're running efficiently. They don't seem to have issues. But for an even larger number of our customers, when there's something small or those transient issues, and all of these interdependencies really present us with a lot of challenges. And if we look at what it takes to kind of unwrap and try to diagnose what a lot of those issues are, the biggest challenge that we have is actually in the data itself. So the data really causes us a lot of problems. And it's for really a number of reasons. And the first one is, in a lot of times, data is very costly. So if you think about generating SMF data or IMS log data, a lot of that requires significant CPU and storage to go and collect and analyze that data. So Kix is generating in a lot of cases thousands of records per second. And if we look at that amount of data, it's very noisy to try to go and find that needle in a haystack to get down to the root cause of a lot of our performance issues. The other thing that we have that is really a big problem, and one of the things that a lot of the log analysis platforms have really tried to go and solve is the fact that data is siloed. And we can get an awful lot of information around Kix, but how does that relate to what's going on in ZOS or DB2? We can bring data together, but it's not truly correlated without us having the intelligence built in to go and take a look at that. So we really have this challenge of the data that we have is very voluminous, but it's not really that enriched data that we need to go and solve and diagnose problems. For a large number of years, RMF data has been around, and it's extremely valuable data for us, but it's not really good at kind of diagnosing those transient performance issues. You know, one of the biggest reasons for that is RMF data is very infrequently sampled. So having data generated every 15 minutes is not going to be frequent enough for us to go and find out what those issues are in our workloads. A lot of those 15-minute intervals will go and summarize right over small spikes or small changes that we're seeing within our workloads. We really can't go and diagnose those problems. So if we're looking at those narrow band performance issues, RMF is not really the best data source to go and do that. It's really sweet spot is really around kind of those long-term system performance and capacity planning use cases. So a little over a year or so ago now, we announced the IBM Z15, and I was just talking to about a customer in about a half an hour ago that's actually rolling out some of their Z15s. And one of the things that came out with this release of the new hardware was a statement of direction. And it was really around the solutions that IBM has built to solve this problem. And it was IBM's intention to deliver ZOS and middleware interdependency data generation and automated ZOS cross-stack analytics to reduce skill requirements and time required to perform problem identification. And this is really the value that we wanted to bring to our customers. I know this is near and dear to Dan's heart since he lives through this on a day-to-day basis, working with many customers across the globe. So with this statement of direction, IBM actually announced 2 new solutions in January and February of this year. Unfortunately, right at the start of the global pandemic that's keeping all of us out of the UK. So let's start to walk through the 2 pieces that we'll go and talk a bit about in more detail. The first one is the ZOS workload interaction correlator. So if we talked about what one of the biggest challenges to solve diagnosing those system workloads, the first problem was data, and that's really where the workload interaction correlator comes into play. It was really built to solve that data problem, and the whole premise and idea behind it is that it will generate standardized, synchronized, smarter data every 5 seconds, and it'll do that by generating a very high value and consumable data, but a very low data generation cost. And one of the things that always comes up is, well, what is the cost to go and do this? So we know that putting in IMS log exits costs overhead, or generating KICS 110 records is a lot of overhead. In the lab tests for generating correlator data, it was really not measurable, the amount of additional processing required to go and generate this data. So it's truly low overhead or next to no cost to generate the data. And what it's doing is putting out summarized records every 5 seconds. And those summarized records are enriched with a lot of information. So being time sequenced, we can go and take that data and understand, what those very short-term patterns of behavior are. We can look for specific patterns of running across the entire stack within ZOS, within IMS, and look for certain activities or spikes in CPU or response times, and how they all correlate across the different subsystem stacks. So what we do is we break that data down into a set of what we call workload dimensions, or we can see the little cubes that are there. And the workload dimensions that all of that data is kind of standardized around is core type, is the workload component that's running on the core processors, or they're running on zips. What job size is this related to? And the ranges go from tiny up through large, as well as job priority. So are they discretionary jobs that are running, or are these critical jobs within our workload? And what we do is we organize all of those things that are running across the entire software stack by those workload components. There's also, as we get into the demo, we'll see that there's some global processes that are running as well. But what we can do is enable the entire stack of everything that's running on ZOS to gain those connectivity and interconnectivity patterns through a common analytics engine. So if we think of the correlator as solving that data generation problem, we need something to be able to go and analyze that data and information. And this is where IBM has announced the ZOS Workload Interaction Navigator. And this is really the UI that runs and takes all of the data that comes from the workload interaction correlator and analyzes that to to produce a set of key insights. So the navigator runs as an application inside of Zoe. So hopefully everyone here is by now familiar with the Zoe application. And really what the navigator is doing is looking across the entire workload stack to look for multi-domain anomalous activities. So we might see a drop in or a spike in CPU for something that's happening in ZOS, and correspond that to a drop in response times for, or an increase in response times for KICS or IMS transactions. And what this really lets us do is go and identify those cause and victim relationships. So if we have something that's running within KICS, and we might be seeing an increase in response times, our monitors might go out and say, hey, we're seeing a problem within CICS. Our natural tendency is going to go out and do a deep dive in looking at KICS, but it might not actually be KICS that is the problem. So what the navigator lets us do is correlate all of those activities that kind of those same signatures and patterns. And this is what Dan will kind of go through and show us. But we take the data that gets generated from the correlator, and we analyze only a 15-minute window of data and information. And this lets us take a look at that small slice and look for those very transient things that are happening across the workload stack. And what it's looking for are those little peaks or anomalies within that data. Tries to match if we're seeing those peaks across different activities, whether it be ZOS or KICS or IMS, and correlate those to where we have similar patterns into activity groups. So we can start to cycle through those activity groups, and the navigator has the smarts built in to where it'll bring forward the highest value or most exceptional ones first, so that we can really start to deep dive into what the problems are across the workload. And we can, if we think of really where the navigator kind of fits in within how folks would go and use it across operations, if we see and diagnose a problem, this will really let us get down to root cause without going down and chasing, is it a problem in DB2, or is it really a problem in KICS, where it's really something else that's going on in the workload. There is another benefit that the navigator will let us do, and that's going and comparing two distinct time intervals. And what this lets us do is validate that any changes that we've made to the environment have the desired effect that we have. So we can go and say, hey, if we're going and updating an application, are we seeing the same kind of workload patterns and behaviors before and after we made that application change? Or maybe we're doing a software upgrade. We can go and again look at what those workload behaviors and patterns are. And the kind of unique thing, as I mentioned, that this is really doing is really looking at that very short time interval and window of what's going on to really kind of bring all of those corresponding cubes again together into those various activity groups. So this is really meant to be a great SME type tool where we can go and really get down to everything that's going on across that workload stack. So with that, let me go ahead and turn it over to Dan to drive us through a quick solution demo. So I talked a little bit about the solution at a high level. It becomes much more apparent into really what it's doing as we go through and actually see it in action. So I'm going to go ahead and stop sharing and turn it over to Dan to drive us through a demo.
Okay, thanks, Dan. I'm going to get the screen sharing up here. Let's see. So screen sharing says it's up. Can you guys see this?
I can see it, Dan.
All right, great. All right. So, hi, my name is Dan Rosa. Thanks, Dan Wiggin, for, going through correlator and navigator, overview section. I'm going to take you through a demo. So, I do design and development on the workload interaction correlator, or we're going to call it the correlator for short, or in the IBM ZOS workload interaction navigator, or navigator for short. I am also a part-time performance analyst who regularly uses correlator and navigator to diagnose workload performance problems in the lab, as well as for clients that send in data and they have problems, for their workloads. So today we're going to walk through a demo of navigator analysis of correlator data to show how we're using navigator analysis to diagnose a workload performance problem. So we're going to start with the reported problem symptom, and then we're going to walk through this demo about how we can understand get a better idea of what's going on in the workload with the navigator analysis of correlator data. So the problem symptom is for an IBM benchmark. A problem was reported that in a RMF 5-minute interval, 2% of the transactions had a response time between 2 and 4 times longer than the other 98% of the transactions. The benchmark was designed to be repeatable, so the response times are expected to be consistent throughout the workload, but they're not. So Dan talked a bit about, the correlator data generation, just, to level set about some of the things we're going to be seeing in the navigator demo. Correlator data generation, as Dan mentioned, standardizes and synchronizes summary and exceptional data every 5 seconds. How it does this is that within a 5-second interval, correlator data generation participants instrument activities at the job level. And so they instrument, what's going on for their particular component of interest. So we have data produced for ZOS supervisor, for CICS, and for IMS in this data. And at the end of a 5-second interval, what happens is correlator data generation groups similar jobs based on job priorities and job size into something called what we call a workload component. So workload component, if you remember from Dan Wiggins' charts, was basically the cubes. And the cubes had some dimensions associated with it. One of those dimensions was job priority, where we had job priorities of critical, high, low, discretionary, and all. And those job priorities are based on WLM policy importance levels. There was another dimension for job size, and job size values were large, medium, small, tiny, and all, which were based on CPU use relative to the total workload CPU use. So what happens is that at the end of a 5-second interval, similar jobs with similar job priority and job size characteristics are grouped together, and their activities are summarized on a workload component or a cube basis. So at the end of that, as part of that data generation every 5 seconds, every one of those activities also has a worst offending exceptional job and its job activity for each of those workload component activities. So really what correlator data generation is providing is it's providing an information architecture for analytics ready, high value, low cost data. And it does that by standardizing independent multi-component data using that common software stack context of job priority, job size, and core types. So I've loaded here the navigator with the 5-minute data from the workload that had a performance problem. And when the navigator initially loads the data, we can see that we have, time along the x-axis, and we have along the y-axis, we have the CPU utilization by job priority. We can see the average CPU utilization is 88% utilization. At the top line here, we've got some summary data about, just general information about what file is being analyzed, the interval, start and end, system name, as well as some configuration information. For here, we know we have 16 vertical high standard CPUs. So this workload was running 16 processors when it was when it was running the workload. So going back to the graph, we have CPU utilization by job priority. Average utilization across the entire 5-minute interval is 88%. And by hovering my mouse over the graph, I can get, we said that correlator data generation generates data every 5 seconds. We can see what the average CPU utilization is every 5 seconds just by dragging my mouse over the graph. The CPU utilization is presented as a stacked graph by job priority. So you can see here, I can't, if I could get rid of this. No. Oh, here we go. Get that out of the way. So we can see here that we have critical job priority. We've got high job priority and low job priority work presented as a stacked graph. And at the top of this graph represents the CPU utilization across all of those job priorities. There's no discretionary work in this workload. But what we can see here by looking at this graph is that there's some patterns in the CPU utilization where about every 60 seconds or so, the CPU utilization looks like it goes down, drops. Normally it's about 88% utilization overall, but it drops down to about 85% utilization at every one of these CPU utilization values, which happens about every 60 seconds. So basically the Navigator has an automated analysis capability built into the technology. And the idea behind automated analysis is that we really want the analyst to be brought to the data that they should go take a look at for the anomalies in this particular workload. So I'm going to click the automated analysis button to kick off automated analysis. And basically what automated analysis does is that it's going to go and analyze all of the correlator data that was presented to the Navigator for this 5-minute interval in this case. And we talked about that we've got a bunch of activities in each workload component or cube that we saw on Dan Wigan's chart. And basically what automated analysis does is that it establishes a baseline for every activity in every workload component for all the correlator data. And it recognizes anomalies in that data. And so anomalies are just, significant deviations from normal. And for all of the activities that were identified as anomalous, the Navigator will temporally correlate those activities into groups, and then it will prioritize the groups and the activities within those groups to show an analyst an organized progression of interacting anomalous activities that are deviating from normal at the same time. So automated analysis in this example found 13 activities that are worth investigating. And of those 13 activities, it presents data about correlated activity group 1. So this is the first group of activities which are deviating from normal at the same time. Correlated activity group 1 has 11 of the 13 anomalous activities in this first group. And we're going to go take a look at some of the highlights of the anomalous activities in this group and how we're using Navigator data to go diagnose what's going on for this particular problem. So one of the things that the Navigator does in prioritizing activities is that the Navigator there's a concept of some activities are more important than other activities. There are some activities which impact the whole workload. Those are called global activities. Global activities appear first in a correlated activity group. So we have a workload component of CP all. So if something happens in there that affects the whole workload. There's also individual activities that don't have a workload component but are effectively workload-wide. Then we also have and then there are activities that are workload component specific. So that means that they affect one of the cubes on Dan Wigan's chart. So this first one is for CP critical medium. So that's a particular cube. And then the list of global activities and workload component activities are then organized by, ordered by activity volatility. So activity volatility is just, it's a mathematical representation of how much an activity is deviating from normal. So as you can see, I hovered over my mouse over activity volatility, and it presented some help text about, what activity volatility means. So you can get some information about, what these various column headers are just by hovering your mouse over it to quickly remind you of what this information is. So getting back to first anomalous activity, we can see here that we're looking at activity ID 1, and it loaded activity ID 1 in the graph. We're looking at response time per transaction from CICS. So this is a CICS activity, and response time per transaction, it's a global activity from the CP all workload component. And automated analysis graphed response time per transaction as the solid yellow line in this graph. And there's some other points of interest here. The horizontal dashed lines are the range of what the navigator identified as normal, or what it thinks is, the normal baseline, so to speak. And points above or below, outside of those dashed lines, can be are considered points that can be anomalous. And the navigator has algorithms to go figure out, well, which points outside those lines are anomalous. And the navigator, in this particular case, he has temporally correlated activities that are anomalous at the same time in correlated activity group 1. These red vertical lines represent the correlation points that resulted in the anomalies that resulted in a particular activity being included in this group. So this red line and this red line is what brought this activity in the group. And we're going to see as we go through other activities that they're going to have points in common with these two red vertical bars we're seeing. So basically what the navigator is showing in this case is that, hey, at every one of these CPU utilization valleys, there is a spike in response time per transaction from CICS. You can see normally here that the response time per transaction is, around 35 milliseconds. And we can see what's happening overall for the CP all workload component. We also have broken it down into the most exceptional CICS job, which is CICS MAOR by the pure job name, and its response time per transaction. For CICS data, we also have the most exceptional CICS transaction ID, which is TAN2 in this case. So the most exceptional CICS region and transaction ID were identified as the CICS region and CICS transaction ID with the largest response time. So we can see from this data, normally the average response time is about 35 milliseconds, but at each one of these CPU valleys, you've got spikes that are going up to, in this case, 140 milliseconds, 146. So it's the CICS response times have basically gone up, 3 to 4 times from what they normally are. And that's true for the exceptional CICS region, that was most exceptional CICS region, and transaction ID that was also identified. So if you look closely here, you can see that some IDs between 1 and 11 are missing. A navigator can groups together activities that look the same, and it contracts them. So we're going to uncontract those rows. So I'm going to click this contracted row, and now we're going to see that activity IDs 2 and 3 have now shown up. And I'm going to take us to activity ID 3 just by clicking on it. So take a mental picture here of what the graph looks like for activity ID 1. And I'm going to click activity ID 3. And you're going to see that the pattern looks very similar to what we saw in activity ID 1. And by clicking on activity ID 3, now we totally changed which component of the operating system we're looking at. We were looking at kicks in the previous activity. Now we're looking at IMS, and we can also see that there's spikes in the IMS response time per transaction at every one of these CPU utilization values. If you hover over the graph, we can get more information about it. We can see that IMS, we have, we're looking at CPU all workload component for IMS again, and IMS has a response time of about around 5 milliseconds normally, but at each one of these CPU values, it's close to doubling. It gets up to about 8 milliseconds. So similar to CICS, we have for IMS, we have the most exceptional IMS region, and it's the response time per transaction for the IMS transactions that went through that IMS region. So basically from this data, we can see that at each one of these CPU utilization values, we can see that there are spikes in CICS and IMS response time per transaction. So I'm going to click the next button to go to the next activity, which is global spin contention time. That's from ZOS supervisor. And so, global spin contention time, it's one of those ZOS internals it's not internal, but it basically is talking about contention on system resources that is occurring. You can see here that at every one of these, there's normal activity for what contention is on system resources, but at every one of these CPU utilization values, there is an increase in resource contention on some system resource. So hovering over the graph here, we can see that normally, the contention is on the RSMQ resource, but at every one of these CPU utilization values, we have a change in what the contention is on. Contention changes at every one of these CPU values to the RSM AD lock. It also increases, so that means that the RSM AD lock is experiencing more contention on this system resource at every one of these CPU utilization values. So you might say, well, what can I do with this information? Well, so in ZOS, the RSM AD lock, ZOS has address spaces or jobs running in the system, and every address space or job has its own RSM AD lock resource. So the RSM AD lock serializes private storage in an address space or a job. So by having contention on the RSM AD lock, it means that one or more address spaces in the system at the CPU utilization values are having more contention on the RSM AD lock than they had otherwise. So that means that there is contention on private storage going on at each one of these CPU utilization values. And the navigator is going to give us some insights about well, what address spaces are contending on those resources. So I'm going to click the next button to get to the next activity. So The next activity is consumer spin contention time. So we had the previous activity was global spin contention time. This is consumer spin contention time is, well, who is spinning on system resources? So just to backtrack a little bit, so the contention time on those spin contention time resources basically means that, when there's a request for a system resource, that's a spin resource and it's not available, the CPU basically has to spin to get that resource. So the idea is that, at the time that there's global spin contention time going on, there are processor units that are spinning the CPU waiting for a resource to become available. So it's not a productive use of CPU resource. And so, minimizing contention time is always good, but minimizing spin contention time is also, good. So consumer spin contention time identifies, well, which jobs are actually, experiencing spin contention time. So the navigator found that, the CP critical medium bucket had some anomalies for consumer spin contention time that an analyst should be made aware of. And we can see here that every one of these CPU values, we have spikes in consumer spin contention time. If you hover over the graph, if I hover over the graph, you can see that normally CPU spin contention time is a pretty low number. It's less than 10 milliseconds, sorry. And at every one of these CPU utilization valleys, there's a significant spike, and it spikes up to, in this case, 500 milliseconds per second. And hovering over the graph here, we can see here that a lot of that contention comes from, well, a lot of that spin contention is originating from the CQS IFA address space. CQS IFA 2 address space is one of the IMS common queue server address spaces. So it's involved in doing IMS message processing. And at every one of those CPU utilization values, there is contention on resources for the common queue server address space. And in this case, it's correlated with the RSMA DLock contention. So you can say, well, CQS IFA common queue server address space is experiencing contention on its RSMA DLock at these CPU utilization valleys. If you click the See More button, we can get some more information about where the contention is, consumer spin contention time is, and we have it broken down by workload component. So we can see for the CP all workload component represents 100% of the consumer spin contention time across all of the workload components. And then we can see for CP critical all has 94% of the consumer spin contention time is in the CP critical all group. And we happen to be looking at the CP critical medium cube or workload component, which had 22% of the consumer spin contention time, and the most significant job was the CQS IFA2 address space. So, the navigator has some built-in things where we can, easily navigate around to other areas. We can click different workload component. I can see what's going on for CP critical large if I want to, and get back to CP critical medium, which was what we're looking at. Resume automated analysis to get back to where I was, which is, activity ID 6. And so, there's a bunch of ways you can navigate this data. Certainly automated analysis is the first place to go. There are ways that you can manually navigate data as well. I was, doing some of the highlights about how you can go get to other related activities. The C interdependent activities, you can also pop up and say, well, the consumer spin contention time is related to global spin contention time, and you can click on one of those activities and jump to that if you want to see related activities. So the navigator has a lot of just easy navigation to be able to get to other activities that are related. The last activity that we're going to look at is activity ID 7, consumer spin contention time for the CP critical medium bucket. And if you look really closely at this graph, you can see that, at least for the first 4 intervals, it looks like there is a spike in consumer spin contention time 1 interval before every one of these CPU utilization values. And hovering over the graph, we can see that those spikes are occurring in the IXG logger address space. So the IXG logger address space is the ZOS address space that does logging activities. And so what's interesting about this is that, it occurs 1 interval before every one of these CPU utilization values for at least the first 4 intervals. And there's some question about, well, it looks like there's some spikes here as well for these, last 4 intervals, but it's not clear. Well, did it occur? Is it consistently 1 interval before the spikes we saw for the other activities? So one of the things the navigator lets you do is says, well, you can pin an activity and compare it to another activity. So we're going to pin the consumer spin contention time for CP critical small. So that's pinned to the graph. And now I'm going to go jump to, we'll jump to the response time for CICS by clicking on it. And we can see here that, now we've got both graphs on the same page, on the same screen. We can see that, consistently we've got a spike. We've got consistently a spike in consumer spin contention time originating from the IXG logger address space 1 interval before we have these response time per transaction spikes in CICS and IMS. So basically, through navigator analysis, we were able to quickly identify, the workload components that are interacting for this particular performance problem. We saw it was right in the data, right in the first correlated activity group. We had response time per transaction peaks in CICS. Well, first thing we had was CPU utilization valleys. Then we had at every one of those CPU utilization valleys, we saw response time per transaction peaks in CICS and IMS. We saw peaks in global spin contention time on the RSM AD lock. And we saw contention occurring on those spin contention resources from the IMS common queue server address space. And 1 interval before all of those peaks, we happen to see that there also was spin contention originating from the IXG logger address space. So our working theory at this time is that the IXG logger address space is doing some kind of periodic activity under the IMS common queue server logging activities, and that is causing and that's somehow triggering contention in IMS common queue server and RSM AD lock contention, which later drives IMS response times and CICS response time spikes. So basically with navigator analysis, we're really able to get an X-ray into what's going on in the workload. So we have CICS data instrumented, we have IMS data instrumented, we have ZOS supervisor data instrumented, which gets us a view on what's going on for CPU resource use across the workload, as well as some of the system resources that various ZOS services that middleware products and other ZOS components are using. And so we can use navigator analysis to get insights into what areas, what ZOS workload components, what middleware products are are involved in a particular performance problem, so we can implicate and exonerate components of the workload and identify focus areas of, here's the subject matter experts that we need to go engage for this particular problem to drill down further into what's happening. We also use navigator analysis to identify when should we be looking, right? It clearly, we have navigator correlator data, navigator analysis tells us, 5-second interval, 5-second interval where things are not running well at all the, CPU utilization at all the peaks, and when things are running well, and we use those 5-second timestamps for correlation with other data to say, well, when are things running well, when are things running poorly, so we can get a better understanding of, what is behind, the root cause of what's driving this transient workload performance problem that we're seeing. So right now we're in the process of grabbing further data from IMS Common Q Server and IXG Logger to further diagnose what's going on here. And basically, when we identify it, then we're going to look into what workload configuration changes can we make to mitigate this problem. What knobs can we tune in the stack to improve the results, and what kinds of opportunities do we have in future development to improve the results for this particular workload. So, with that, that's the end of the demo, and I'll turn it back over to Dan Wigan.
Yeah, so thanks, Dan. If you can leave your screen up for just one more moment. So just to kind of bring this back to kind of a high level, especially with the things that we have pinned here, if kind of consider that, we might get an alert from one of our resource monitors, or even if we're sending data to an APM solution or to a log analysis solution, that we're seeing the spikes in kicks or IMS in transaction response times. This is really, we could spend an awful lot of time going down and investigating what's happening in kicks or IMS to cause those transient spikes. And it's really because we don't have that deep view of everything that's happening across this. So as Dan went through the demo, it was really the IXG logger that we really need to start looking at as that really the root cause of what we're seeing as symptoms in CICS. So that's really where the navigator is really doing some kind of advanced analytics based on the new data and that new smarter data that we're getting out of the correlator. And just to give a little bit of kind of a time frame of kind of when these solutions came about, and as kind of Dan pointed out, we have data from 3 different sources at the time. We have the supervisor data, we have kicks and IMS, and the solutions were first made available kind of unfortunately right around the start of the pandemic that's keeping us all apart in March. And shortly after that, kicks came along and started generating their own data to adhere to kind of that correlator standard. And then IMS around the June-July timeframe started generating their own data as well. And the expectation and plan is that we'll start seeing the other subsystems come and start bringing in their data as well to really enrich what we're seeing more across the entire workload stack. We can get a lot out of the supervisor information, as Dan showed and mentioned, but the solutions becomes more and more powerful as those additional subsystems come on board. So we have about 10 minutes left. So I'm going to go ahead and go through a couple of other just kind of quick slides just to kind of wrap things up through the session today. And as Dan went through the demonstration, we talked a little bit about anomaly detection, and he was looking for those anomalies that happened across those short time periods. And we talk a lot about anomaly detection in terms of machine learning and AI. And I wanted to really compare how this is really kind of different than what we would see in terms of looking at more of a machine learning solution. And there's actually a session on this that I'll be leading next week as well. But I just wanted to really talk about the differences in the solutions and how we're using data and technology. So what Dan showed in the Navigator is that we're really looking at a short baseline or a short period of information. So just up to 15 minutes worth of data. So we have no prior knowledge of what happened in the system. We don't really know, kind of what happens normally during this period of time. We're really just analyzing that short period of data, where if we look at using solutions like Watson machine learning for ZOS or other anomaly detection engines, they're looking to create a baseline of normal based on historical data. So it's taking months or whatever time period is needed of historical data to build a baseline to understand what your environment is. So two very different things, looking at all of that historical context to understand what to look for versus looking at a very short time box. Once we have that baseline for information, what the ZOS workload interaction navigator is doing, as Dan showed, is looking for those outliers across that data. So we can see all of those different little peaks that were happening that happen to correlate to those drops in CPU, or the little spikes that we saw in the IXG logger, right? So it's looking for those anomalies as compared to kind of what that standard average or median is for that specific activity. Whereas a traditional machine learning solution is looking at taking real-time data and comparing that to what we would normally see for a KPI or a set of KPIs during that same time period based on historical data. So two kind of very different ways of looking at and fleshing out anomalies. So again, the navigator is just looking for those short-term or spikes that happen within that little time box as outliers. So really those transient issues that are happening, or little things that are happening that looking at summarized data might just get ignored or averaged in. It's really good at picking out those very small things that are happening. Whereas again, machine learning solutions are scoring a set of KPIs against a historical baseline and looking for trends and patterns, and often doing a little bit of summarization to kind of smooth out some of the curves that are there. And they really have two very different use cases of what they're going after. The navigator is very good at correlating those short-term anomalies or deviations to identify root cause. So for the example that Dan went through, we saw what we might see as something that would trigger resource monitors like the Omegamons, or with those spikes in CPU, but that really wasn't the problem. It's a deep dive root cause problem determination solution where we can go and see, hey, maybe it was actually the IXG logger that was the problem happening here. Whereas the use case for looking at traditional machine learning solutions is we're looking at trends and patterns where we deviate from normal, with the option or look to become more forecasting in nature of when we might experience a problem. So if we start seeing small deviations and trends away from normal, we can use those machine learning solutions to say, hey, do we expect this to go back down to normal, or do we expect this to keep going and deviating more away from normal where we might see a future problem? So one is very, let's use this technology to go and forecast problems. The other one is really getting down to quickly identifying root cause and mean time to repair. So, using analytics and anomaly detection, but in two very different use cases to go about doing that. So just to summarize on the solution and kind of what we saw today, really two different pieces that fit as the puzzle. The workload interaction correlator, again, fills that gap that we had in data. So it's that very smart, enriched data that gets generated on a very short time sequence every 5 seconds. It's very low cost, so we don't have a lot of overhead to go and generate this. The files that get analyzed by the Navigator UI are quite small. They're several megabytes in size, so we're not talking about storing gigabytes and gigabytes of data to do this kind of deep dive analysis. So really, again, there's two use cases that we have really helping us go in and get down to root cause. And the other one that we really didn't cover as part of this is the Navigator can also compare, again, two different time intervals to see that if we're making changes to our environment, that we actually see similar behaviors, and that we can go and validate that the changes that we're making don't have negative impacts to our workload. So we're not seeing, a big jump in CPU utilization after we apply maintenance or a fixed pack, or even if we make a small change on a distributed application that has APIs back into the mainframe, we're not seeing, a lot of different or changes in resource consumption as a result of that. So it's not always needed to go through and do a problem and looking at root cause problem determination. So a couple of great uses, and really this really lets you kind of, even in a general case, just really understand at a deep level exactly what's happening across your systems and that's consuming all of the different resources. So in the slide deck, there's a couple of links out to the announcements and pages for more information. There was a systems article on this in one of the recent IBM Systems magazines to go and find out a little bit more information there. We ask you to go out and fill out the survey for this session. Really a lot of great information, and largely I want to thank Dan for going through the great demo and deep dive into really what the solution looks like. I know he lives through this on a day-to-day basis, and it's really getting the value out of that is hard to capture in a few slides. That's really why we wanted to come through and do the presentation today. Just a note about the GSE UK charity that's here. And with that, I'll go ahead and take a look at the chat for any questions that may have come in.
Okay, so there's no questions actually in the chat, but I have given each of you the ability to unmute yourself if you have any questions you want to pose to the Dans. Okay, well, I like to thank the Dans for their time, and for all of you for your time to participate. And please don't forget to fill in the feedback. It'll help us for next year's conference. I will end the session now, unless anybody quickly jumps in to stop me doing it. Okay.
Thank you, Anna. I hope everyone has a great rest of their days.
Yep. I'm quite looking forward to the keynote a little later today. So, okay, in about an hour or so. Take care, everyone. Stay safe. Bye.